In this video, we will begin our lecture with the topic of z-test for the true population mean. The handout that I gave in class with the basic concepts and foundation of hypothesis testing consisted of this particular page, the second page on the traditional method and the p-value method, and then the page of phrases which help you find the correct symbol, and lastly, the summary diagram so that you can make the correct decision and summary statement. And I have the test statistic formulas here also. The rest of the handout pertains to the z-table, the t-table, and the chi-square table. I spoke briefly about the entire concept of hypothesis testing in class, and we mainly focused on traditional methods, which is here, and it's also stated on the next page. We talked about the definition, which is the process of evaluating claims made about population parameters, mu, rho, sigma, sigma squared. Samples, once again, are used to investigate the claims. Based on what is learned from the sample, information is inferred upon the overall population. This is once again inferential statistics, and we will only be a certain percentage confident that our decisions and summary statements are indeed factual, just like with confidence intervals. We talked about how in the traditional method they ask us to set up our hypotheses, the null and the alternative, and that there's only 3 ways to set up the hypothesis. So there's only 3 ways that you can actually set up step number 1. We talked about how even though I put the parameter mu here, we can replace it with rho when we do our proportion testing. We can replace it with sigma when we do our chi-square testing for true standard deviation. We can replace it with sigma squared when we do our chi-square testing for true population variance. So you can still have this on your test and just know when you need to replace your parameter. It depends upon which parameter that you're testing or the claim that is made about which population parameter, and then you can change it here. But in terms of the symbols, equal to, not equal to, less than or equal to versus greater than or equal to versus less than, they do not change. Only the parameter is allowed to change. The null and the alternative are never switched. You cannot switch those. They have to be stated just like the handout here. If you notice, the alternative never has equality, not equal to, greater than, less than. The null statement either has equal to, less than or equal to, greater than or equal to. The claim can be the null or the alternative, but not both at the very same time. When you make your decision in step 4, you either reject the null or do not reject the null hypothesis, so the decision is always about the null hypothesis. And the summary statements. The summary statements are always about the claim. Remember, the claim can be the null or the alternative, but not both at the same time. It's one or the other, because these statements do not overlap. They are opposites each other. So your summaries depend upon the claim, what you're testing, the claim about the population parameter. And therefore, in summary, your summary is always about your claim statement. Decision, you reject the null or do not reject the null, but the summary statement is always about the claim. Now, there are errors in hypothesis testing. There's always a possibility that you made the wrong decision in rejecting the null or not rejecting the null. I tell students that the best way to know what type of possible error you're making is to realize what your decision was in step 4. If your decision was to reject the null hypothesis, then the possibility you made a mistake was a type 1 error or alpha. Rejecting something that's actually true would be a mistake. If your decision in step 4 is to not reject the null hypothesis, you can still make a mistake by not rejecting it. What if you do not reject it and it was actually false? So that's a type 2 error or a beta error there. We went over quite a few other items in class in terms of the general overview, but we did not complete a problem together. This is the traditional versus the p-value method. Once again, they're going to agree with step 1, stating the hypotheses, identifying the claim. They are going to agree when it comes to decision time, the decision is going to be the same regardless of method, and the conclusion or summary statement is going to be the same regardless of method. So for most of the problems that we have, and we have 8 of those, we have it as a traditional method versus a p-value method. So I would like to get started in this video on the z-testing problem for the mean. Remember, I represent 2 z-test problems for the mean, and so there's a third option that I'm not representing because each test can be two-tailed, right-tailed, or left-tailed. There are 3 ways to conduct a z-test for the mean. I'm only going to do 2 problems representing 2 out of the 3 ways. So let's read the problem. Often it is very important to take a highlighter and pick out what is given so that you can identify the claim. Hypothesis testing problems for class. Operating cost of an automobile. The average cost of owning and operating an automobile is $8,121 per 15,000 miles, including fixed and variable costs, period. The most important information from that sentence is that the average cost of owning and operating an automobile is $8,121. A random survey of 40 automobile owners revealed an average cost of $8,350 with a population standard deviation of 750. And then here's the last statement or question. Is there sufficient evidence to conclude that the average is greater than 8121? Let alpha be 1%. Now, alpha is what the researcher sets in this hypothesis testing situation. Alpha is the probability of a type 1 error rejecting the null when it could have been true. Remember, a type 1 error is called level of significance at which we are going to conduct our test. It is the probability of a type 1 error rejecting the null when it could have been true, which we'll never know. But it's still the possibility that we made a mistake in rejecting the null when it could have been true. So we're going to need alpha to conduct this test, and it's only as small as 1%. Now, I'm going to write down the given information in the packet here. First of all, they survey 40 automobile owners, and they found out their average cost was $8,350. For some reason, they didn't get the standard deviation from the 40 automobile owners, but they used a population standard deviation, sigma, of 750. And then alpha's 1%. The question is there sufficient evidence to conclude that the average is greater than 8121? So the next thing we want to pick out or point out is that this would be a z-test for the mean, and I'm going to write that over here. Because sigma is known. In terms of our subconditions, it doesn't matter if they say the population of the people owning and operating an automobile is normal, because our sample size is large enough to go ahead and conduct this z-test for the mean. And then sigma is known. So it's a z, not a t. And that means it's a z-test, we'll be using the z-table for anything we need to do here, table-wise. Next thing we need to do is I always look at what they say in the first sentence of these problems and what they are saying in the first sentence. They're saying that the average cost, mu, is 8121. Is a statement that means equal to. The question is, down here, is there sufficient evidence to conclude that the average is greater than? So average greater than, not greater than or equal to, greater than 8121. So that statement is mu greater than 8121. And this first sentence, mu is equal to 8121. The first sentence and what I call the last sentence, even though alpha equals 0.01 is technically the last sentence, the first sentence and the last sentence disagree. So one is the claim that we're testing, and the other is the statement opposite the claim. So to really read the problem and understand which one of the two we're testing, which one of the two would be the claim, we have to go by the question, is there sufficient evidence to conclude that the average is greater than 8121? So mu greater than 8121 is the claim. We are not testing the first sentence. It's just stated maybe from a magazine or somewhere online, somewhere from someone that's conducted some type of test that the average cost of owning operating an automobile is 8121. But is there sufficient evidence to conclude that the average is greater than 8121? That's what we're testing. Now, I did the first sentence thing and the second or last sentence, and they did disagree. Whenever they disagree, one statement is a claim, and that's what you're testing. The other statement is opposite the claim. I'd also like to tell you that one statement or one sentence is either your null or your alternative. So one is the null, one is the alternative because they're exact opposites of each other. Now, with that being said, this happens most of the time that the first sentence and next to the last sentence or the last sentence disagree. One is the null, one is the alternative, and obviously out of the two, one of them has to be the claim, which is what you're testing. There are times when both the first sentence and the next to the last sentence are the same, and that means that they've stated the claim twice. They stated it at the beginning and they stated it at the end, and they agree in terms of statement of the claim, and the symbols also would be the same. That's rare, but sometimes that does happen. Most of the time, though, you have exact opposite statements. And there's no big deal if they are the same and the claim is stated twice, because once we know the claim, we will be easy, and it'll be easy to do the following. Take that symbol, and you have to know what greater than means. And if you don't, then the whole point of that is to go to your phrase sheet. So we are testing greater than, so that's our symbol. And then we got to set up our problem. There's only one place out of the 6 symbols greater than is going to happen, and that is the alternative statement here for this particular test. Cut this out with a pair of scissors and a glue stick and paste it down on your paper. So this is going to be mu less than or equal to 8121. Mu greater than 8121. And I like to say that the claim is the alternative hypothesis. And again, I took my claim symbol. I'm writing on a different sheet. Let me go back to this particular page. I took my claim symbol and I found it in the listing of possibilities. It only occurred in the place where the alternative was greater than and the null was less than or equal to. And then the magic number is 8121. That's the claim number. And the claim is the alternative. Now we can go back and give our z-test a more specific name. Not only is a z-test for the mean, but it is right-tailed. How do you know it's right-tailed? All you have to do is come back here. Since this was your claim symbol and it's obviously the alternative, then it's right-tailed. Greater than points to the right, so it's a right-tailed test. In terms of sentences for this problem, it turns out that this null statement is involving that first sentence. Now, I know the first sentence says exactly equal to 8121, but that is still opposite the claim. The last sentence, which is what we're testing, because it says, is there evidence to conclude that the average is greater than 8121? That's how we know that's what we're testing. The alternative is the last sentence. So this is the case where the first sentence and the last sentence are opposites. One sentence is the null, one sentence is the alternative, and out of the two, only one of them can be the claim. Just so happens here in this problem, the claim is the alternative hypothesis. It's very important to know that. Critical values are determined by the alpha in which you're testing this hypothesis. And you also have to know what type of test you're dealing with, because you're going to draw a z-axis and go back to the standard normal distribution. And you are going to shade the right tail because it's a right-tailed z-test for the true mean. That alpha is here in the right tail. So that means there's 99% area below this z. You could do invert norm with your calculator quickly. Put in 0.99 and you get 2.33. That is going to be called something called your critical value. So I would like to put it here on the axis, 2.33. And a lot of times CV is equal to 2.33. This critical value is so important because it marks the non-shaded region from the shaded region. The non-shaded region is called the non-shaded, non-critical, non-rejection region. The shaded right tail, because it's a right-tailed test, that's why I shaded the right tail, and that's all of the given alpha to find that critical value. This is called the shaded region, the critical region, the rejection region. And we're going to use this picture to help us to make our decision in the traditional method. Test statistic time. Z is equal to x bar minus my claim number, sigma over the square root of n. That's going to be $8,350 minus $8,121, all over $750 divided by the square root of 40. Okay, so if you want to put this into your calculator in one single step, you would begin with parentheses around the 8,350 minus the 8121 divided by parentheses 750 divided by the square root of 40. And press enter. If you round to two places because it's a z-score, it's 1.93. So this test statistic is 1.93. Now, my favorite part. To make the decision, you take your test statistic of 1.93 and you put it on the z-axis where it should fall. 1.93 is smaller than my 2.33, so if it fell on the axis anywhere, it would be here. And when the test statistic falls in the non-shaded, non-critical, non-rejection region, they say, do not reject the null hypothesis. And I like to restate what the null says. The null said that the average was less than or equal to 8121. Do not reject the null hypothesis because the test statistic fell in the non-rejection region. If you have a test statistic that is larger than this critical value, like a 2.58 or something like that, then you would reject the null statement. So remember, decision, you either reject the null or do not reject the null. Only two ways to state the decision. With the traditional method, if the test statistic falls in the non-shaded, non-critical, non-rejection region, do not reject the null. If the test statistic is larger than your critical value, which means it falls in the right tail on the axis, you would reject the null hypothesis. Summary statement. Once you know that your claim is the alternative, You've got two choices. In your word problem, is your claim the null statement or is your claim the alternative? Our claim was the alternative, that the average is greater than 8121. That's what we were testing. And then you need to decide, step 4, what did you do with the decision? Do not reject the null hypothesis. Here is step 5. So all the way back up at step 1 is when you are deciding what you're testing. Was it the null or was it the alternative? In this problem, it was the alternative. Step 4, do not reject the null. So here we go. There's not enough evidence to support the claim that the average is greater than 8121. So I'm going to go to the paper, and you would write that in the step. There is not enough evidence to support the claim that, and because I want to save space, I'll say mu is greater than 8121. There's not enough evidence to support the claim that the average is greater than 8121. So let's think about what that means. Going back to the very beginning, we have this statement that the average cost of owning and operating an automobile is $8,121. A random survey of 40 automobile owners revealed an average cost. They spent $8,350, and they used a population standard deviation of 750. The question says, is there sufficient evidence to conclude that the average is greater than 8121? So that's what we're testing. We believe that it's greater than 8121, which is against what they say in the very beginning, the first statement, the first sentence. So greater than is actually an alternative statement if you follow your possible two-tailed, right-tailed, left-tailed. The null statement in this case is the first sentence where there's just a blunt statement that it is 8121. But with alpha being 1% level of significance, can we conclude that there's sufficient evidence to support our claim? And basically, no. There is not sufficient evidence to support the claim that the average is greater than 8121. And why is there not sufficient evidence to support that claim? We didn't reject the null statement because that was the first sentence. So if we don't reject that first statement that it is 8121, that means there's not enough evidence to support our claim that said it's greater than 8121. So I'll leave you with that thought. If hypothesis testing is a struggle for you, it is very much a step-by-step process. So if you just want to do what I said about make it structured, read your problem maybe 1 or 2 times, write down the information they give you in terms of sample information, any population information they give you. Analyze the first statement and maybe write it down with your parameter and the symbol. Analyze your last statement or your question at the end or your second to the last sentence or just the last sentence. And you say your parameter and you want to pick out what it says in terms of symbol. And then you will be able to decide which one of the two happen to be what you're going to test. In this case, we're testing greater than. So once you know your claim symbol, it's easy to set up this by just going to locate your claim symbol. So your setup has to look exactly like this. You can't change anything other than change hashtag to 8121. You pick it up and you paste it down here. So the claim is the alternative. We also know we're working with a right-tailed z-test for the mean. We use the z-table to find the critical value 2.33, which is a cutoff, and it's determined by alpha. Remember, alpha is the probability of rejecting the null when it could have been true. For this particular problem, we didn't have a type 1 error. We had a type 2 error. Beta is the probability of not rejecting the null because that's what we did. We did not reject the null when it's actually false. Now, again, we never know this, but what if this happened? We did not reject something that was false, and we should have. So that's the possibility we made a mistake. So you definitely go by your decision in step 4 if you ever want to know what is the possible mistake you made, a type 1, a type 2, or alpha, beta. And so I went by my decision, do not reject the null, but what if it was false? So it's a type 2 error or a beta. Now, the p-value method for this same problem. For this same problem, I basically could, for most of all of this, I could just bring everything over. Mu is less than or equal to 8121 was the first sentence. Mu greater than 8121 was my claim. Last sentence. The test statistic we already calculated as x bar minus mu, sigma over the square root of n, and I'll just put that we got a 1.93. We are going to end up with the same decision and the same summary. But the p-value method is a different way of coming up with my decision. The way that you come up with the decision over here is that you draw your picture, you determine your critical values, which determine your rejection regions and your non-rejection regions. You take your test statistic, you put it in the picture. If the test statistic falls in the non-shaded non-rejection region, do not reject the null. If the test statistic falls in the rejection region, reject the null hypothesis. So it's that simple to make the decision with the traditional method. What we do over here with the p-value method is we find a number that is called a p-value. A p-value is a probability. It's always positive. It's given to 4 decimal places. And it is determined by your test statistic. So I'm going to go through the procedure for finding the p-value. And then I'm going to show you something that I'm going to be sending you as a document to give you an explanation of a p-value. Now, to determine it, you use your z-axis, bell-shaped curve, put your test statistic of 1.93 where it falls. Shade the area that it indicates above it. That area in blue is the p-value. Again, I'm going to give you a definition or explanation of what a p-value means. But for now, just go with the way that you find it from the 2-page z-table because this is a z-test for the true mean. So I put my 1.93 here. You can go back and you can look up a 1.93 in the 2-page z-table. But remember, you're going to get the area below it. So 1.93 looks like to me 0.9732. 0.9732 is the area below it. 0.9732. So I'm going to put that here. Therefore, this is 1 minus 0.9732, and that's going to be your p-value. That's 0.0268. So I'm going to box it, and I'm going to say that's your p-value. P-value. You could also do normal CDF if you remember how to do that. You would go to second variables and go to normal CDF. You'd put in 1.93 and then an E99. And then you would paste. And you get 0.0268 rounded to 4 places accurately. And you could find your p-value that way if you did not want to look up your test statistic in the z-table. Now, decision. Decision is made by comparison with the given level of significance and the p-value that you find. And I want to show you, basically, I always state alpha open box p-value. I never put p-value open box alpha. This is why, if you go to your p-value method, you will see this is how you make the decision. If alpha is larger than or equal to the p-value, reject the null. If alpha is less than p-value, do not reject the null. So that's why I like to do this box p-value, because when it comes to step 4, you're either in the box going to put greater than or equal to, less than. So I always compare that way. And let's go back to this specific problem. What I do is I write my numbers. Remember, alpha was given to be 1%, and the p-value we found was almost 3%. So alpha is definitely smaller than the p-value, and you only have 2 choices for symbols. Remember, you either put greater than or equal to in the box or less than. So I'm putting less than. And according to the paper, if alpha is smaller than the p-value, do not reject the null hypothesis, which I'm just going to draw a double arrow. Do not reject the null hypothesis. And then you could go to your summary diagram, and the fact that our claim is the alternative, but we do not reject the null, then that means there's not enough evidence to support the claim that the average is greater than 8121. Do not reject the null statement. Therefore, we cannot support the claim statement. And that's the conclusion for this problem. Other than showing you the calculator, you would go to Stat and arrow over to Test, and it's number 1 z-test for the true mean. Once again, you have a raw data option and a statistical option. I never use raw data option even if you have a raw data problem. So, mu sub 0, that is your claim number that comes from step 1, 8121. So when our setup said less than or equal to 8121 versus greater than 8121, mu sub 0 is the 8121 in step 1 setup for the right-tailed z-test. Sigma was $750. X bar was $8,350, and they surveyed 40 people. Now this little option, you can arrow over. It says not equal to 8121, right? Because mu sub 0 is 8121. Less than 8121, greater than 8121. This particular statement is asking you to tell the calculator what type of test you conducted. Did you conduct a two-tailed z-test, a left-tailed z-test, or a right-tailed z-test? And how do you determine that? You go back to your paper and you look at your setup, and whatever you determined as your alternative, you have to highlight and then arrow down. So I'm telling the calculator it was right-tailed, greater than 8121. The only thing that the calculator is good for is that test statistic, which you may not like calculating it by that formula, so the calculator could do it for you, 1.93, and the p-value. Now, most of the time, the p-value will agree with the p-value that you get by hand. By the way, this is not row in terms of population proportion. This is the p-value that you use in the p-value method. If you round to 4 places here, you get 0.0267. So I'm going to go back and write that on my paper, but it's not going to make a difference in terms of when you compare alpha and p-value. Alpha is still smaller than this p-value, so do not reject the null hypothesis. It really doesn't give you much information at all. Some students don't even really bother with the calculator that much. I do think it's nice when it can give you a p-value though. Obviously, if I ask you for the p-value, I'm going to be stating that this is the one that you get by hand, and I'm not going to be putting 0.0267 as an answer choice option there. Regardless of which one you use, calculator or the by hand p-value, when you compare, alpha is still smaller, so do not reject the null. So that is problem number 1. Let's go on to the second problem. That was a right-tailed z-test. And for the second problem, so I don't have to flip my pages back so much, I'm going to go ahead and work on this sheet. I promised that I would show you this handout that I'm going to be sending out to you. What is a p-value in layman's terms? And they have it here. The p-value, which we find from the test statistic, is the probability. So it's a probability rounded to 4 places. You can also express it as a percentage. It's always positive. That the null hypothesis is true. Basically, in a nutshell, that's what they're saying. Is the probability that the null hypothesis is true. You can read this when I send it to you, but it's really good. But you will have to read it all. Here's another explanation of what a p-value means to hypothesis testing and what it is. Here it says a p-value is used in hypothesis testing to help you to support or reject the null hypothesis. The p-value is the evidence against a null hypothesis. The smaller the p-value, the stronger the evidence that you should reject the null hypothesis. The smaller the p-value, the stronger the evidence that you should reject the null hypothesis. And when we reject the null hypothesis, alpha is larger than your p-value, and that's because your p-value is so small. Alpha is larger than your p-value, so your decision will be reject the null hypothesis. The larger your p-value is, probability or percentage-wise, the larger it is, the, I guess, least likely or less likely to reject the null. You probably would say do not reject the null. So the larger the p-value, the more support you're going to have for the hypothesis statement. Again, a p-value is used in hypothesis testing to help you support or reject the null. The larger the p-value, you have more support for the null, so do not reject it. The smaller the p-value, the more support for the alternative, or you're going to reject the null. The smaller the p-value, the stronger the evidence that you should reject the null hypothesis. You could also write the larger the p-value, the stronger the evidence that you should not reject the null hypothesis. Again, it's all about a comparison with alpha and p-value. Please do read this statement, especially if you want to know more about p-values and why you're calculating these p-values. This particular statement is also very good. It goes on to the next page and it states a small p-value, less than 5%, usually you would reject the null. And the reason is that your alpha that you're using to test your claim is probably going to be larger than that p-value if it's that small. So if alpha is larger than the p-value, reject the null. If you have a large p-value, larger than 5%, it's probably going to mean that you are the alternative hypothesis is weak, so you do not reject the null. That means that alpha is going to be smaller than the p-value because your p-value is so large that you are not going to reject the null. So a small p-value, reject the null. A large p-value, do not reject the null. But again, you're using alpha to compare it to the p-value to make your decision. Okay, I will be sending that document out. They also have a description in the textbook if you're curious about what a p-value actually represents. Use of disposable cups. Let's read this problem and let's master what it's saying. The average college student goes through 500 disposable cups in a year. Now that can be what we're testing or what we're claiming, but it may not be. To raise environmental awareness, a student group at a large university volunteered to help count how many cups were used by students on their campus. A random sample of 50 students' results found the following. A mean of 476 cups with a standard deviation of 42 cups. Okay. At alpha equals 0.01, is there sufficient evidence to conclude that the mean differs from 500 disposable cups? Okay, so let's look at the first sentence in the paragraph. The average college student goes through 500. It did not say more than or less than, so it's implying that they go through exactly 500. And there is a typo. It should say the average college student goes through an average number of 500 disposable cups in a year. That's what it should say. On average, they use 500 disposable cups in a year. Now, the last statement, or in between, let's write down the sample stuff. A random sample of 50 students found that they used a mean of 476 cups with a standard deviation of 42. Now, they didn't say population standard deviation. They just gave the symbol sigma. So, sigma is 42 cups. And they're testing the claim, whatever it is, we're going to decide in a moment, at 1%. So, last sentence or question, is there sufficient evidence to conclude that the mean differs from 500? So, the mean differs from 500. If you do not know what differs means, you go to your phrases and you will see is not equal to, is different from, has changed from, is no longer the same as. So, differs froms mean not equal to. So this last sentence or question means not equal to. And that's the last sentence. One has to be the null, one has to be the alternative, and only one of the two could be the claim, what we're actually testing. They are opposites. That's why I say one has to be the null, one has to be the alternative. And one of them has to be identified as what we're testing. So, according to the paragraph, it looks like there's a student group that's not believing the statement that they go through 500 disposable cups. They're believing that it's different from 500 disposable cups. So the student group, maybe the SGA or something like that, takes a sample of 50 students, found they used on average 476 cups in a year. They used a population standard deviation probably from another study, and the student group set the alpha to be 1%. So is there sufficient evidence to conclude that the mean differs from 500? The last sentence is your claim. Now, with that being said, follow the claim symbol. And the claim symbol is only one place, not equal to. There is a difference or change, and that's the alternative. That means the null has to be equal to. Cut, paste, glue stick. Mu equals 500. Mu does not equal 500. The claim is the alternative. Hypothesis. So I'm going to name this test. It's a two-tailed z-test for the true mean. Two-tailed z-test for the true mean. And I could draw an arrow over here too for this, or write it. P-value method. They agree. Same problem. Just different ways to make the same decision. So it turns out my null is the first sentence, and my alternative is the last sentence or our question, and the alternative is also our claim. for this problem. Critical values. When you have a two-tailed z-test for the mean, you have two critical values. You will shade the left tail and you will shade the right tail, and you're looking for negative z and positive z to mark your rejection regions. Each tail will be alpha over 2. So alpha was 1% divided by 2 is 0.005 in each tail. Obviously, I feel like the quickest way to find the critical values and there's symmetry going on with this z distribution is to do invert norm on that bottom 0.005. And you get negative 2.58 when you round to 3 places accurately. So the two critical values are plus and minus 2.58. Now I know this cutoff. That marks that critical region, and this positive 2.58 marks this critical region. So CVs are plus and minus 2.58. Again, we have two critical regions because it's a two-tailed z-test. When it was a right-tailed z-test, we shaded the right tail and we had only one critical value and it was positive. Now that it's two-tailed, we shade both tails and we have two critical values, a plus and a minus, and we had to divide alpha by 2. And just so you know, we've just discovered, since this is the last z-test problem in the packet, we just did a right-tailed. We shaded the right tail. That was all of your alpha to give the critical value. Now we're doing a two-tailed. Alpha divided by 2 is the area in each tail, so we find two critical values. If you have a left-tailed z-test, which means you'd have to have this set up, this whole scenario here for a left-tailed z-test, you would shade the left tail, and alpha there would be your given area in that left tail, all of the alpha, and your critical value would be negative using that alpha in the left tail. So z-test, if it's two-tailed, shade two tails, alpha divided by 2. If it's right-tailed, shade the right tail, alpha is all the area in the right tail. If it's left-tailed, shade the left tail, alpha is all of the area in the left tail. And you can use invert norm to find those cutoffs, which determine those critical values. Two critical values, one critical value and it's positive, one critical value and it's negative. Two rejection regions, one rejection region, one rejection region. So that's a pattern you can pick up on. I hope you do anyway. Those are my two critical values. Now the next step is my test statistic, because that's going to help me make my decision. If you don't like to do this by hand, let your calculator do it for you. But that's 476 minus 500, all divided by 42 divided by the square root of 50. And I know it's a negative number because 476 minus 500 is going to be a negative difference there. 476 minus 500. I did enter this time instead of putting parentheses around the numerator. Divided by parentheses, 42 divided by the square root of 50. Arrow out. Negative 4.04 is the test statistic. It's a pretty big test statistic there. Or excuse me, small test statistic. So, where does that negative 4.04 fall? Uh-oh. It is smaller than the negative 2.58 critical value, so it's in the left tail rejection region. So the decision is reject the null statement. Reject the null. Again, I like to write my null statement. Reject the null statement. Remember, you either reject the null or you do not reject the null based on where your test statistic falls. Test statistic fell in the left tail, reject the null. If I had a test statistic that fell anywhere around here in the non-shaded, non-rejection region, you would not reject the null hypothesis. But this one, we reject the null. And then our summary is good news for the student group, because if you go to the fact that the claim by the student group is that it differs from 500, and we just decided to reject the null statement that says it is 500, that leads to claim is the alternative, it differs from 500. Reject the null that says it equals 500. There is enough evidence to support the claim that the average no longer equals 500 or differs from 500. There is enough evidence to support the claim. So the claim was the alternative. We rejected the null. Step 1, step 4, step 5, write it down. There is enough evidence to support the claim that mu differs from 500. There is enough evidence to support the claim. Hooray for the student group. There is enough evidence to support the claim. Now in this case, since we rejected the null, the probability that the student group made a mistake in what they were doing is alpha, rejecting the null when it could have been true, which they'll never know. But it is a type 1 error possibility. Okay, now the p-value method. We've already calculated the test statistic, so I'm just going to draw an arrow and say it's negative 4.04. And then I am going to determine my p-value by putting the negative 4.04 here, and I'm going to shade the area below it. Okay, here's the big surprise. You're going to find that area, and that area is not the p-value because it's a two-tailed z-test. You double that area only because it's a two-tailed z-test. If this were a left-tailed z-test with this same test statistic of negative 4.04, then all of this area would be the p-value. But since this is a two-tailed z-test and this is your test statistic, then you're going to have to find this area and double it. Now, when you go to your z-table and you try to look up something like a negative 4.04, you have to go to your footnote and says for z-values less than negative 3.49, the area below it is 0.0001. So, this is. And then finally, your p-value total for the problem is 0.0002 by hand. By hand. We're going to see what the calculator says in just a moment, but by hand using the table, 0.0002. So on a multiple choice test, if I ask you for the p-value, be careful. I'm going to have the correct answer, A, but I'm also going to have the wrong answer because some of you are going to forget to double it when it's a two-tailed z-test. Double by hand. So be very, and then I'll have other wrong options also, but A is the correct answer there for p-value. Decision time. Alpha box p-value, 0.0002, and the alpha was given to be 1%. So alpha is larger than. Now, again, there's only two symbols to put there. I know it's strictly greater than, but I'm following my master sheet, and you either put in greater than or equal to or less than. When it's greater than or equal to, reject the null hypothesis. Again, that is here. Just go by the sheet, and it tells you the decision. Which we better have the same decision, same summary, everything. Otherwise, we did something wrong with one of the methods. And the summary statement is the same. There is enough evidence to support the student group's claim that the average differs from or no longer equals 500 disposable cups. Okay. Now, p-value by calculator, and then we'll conclude this video on z-testing for the mean. We would go to stat and arrow over to test, and then enter in on z-test. The hypothesized or claim number is 500. The population standard deviation is 42. The sample mean, 476, I believe. Sample size, they sampled 50 students, and the alternative hypothesis not equal to differs from 500 was our alternative statement. So calculate. The test statistic is negative 4.04, same as what we got by hand, but the p-value is nowhere close to what we got by hand and table. It's 5.3338801, and that e negative 5 means times 10 to the power of negative 5. So I'm going to write that down on paper. So you would move your decimal to the left 5 places. And that would be your p-value by calculator. You do not double if you found your p-value with the calculator. The calculator already knows it's a two-tailed z-test, so when they give you the output of this p-value, then it's taken into consideration that it's a two-tailed z-test. So you don't double here, but you would have to double by hand if it's a two-tailed z-test. They are really, really large, obviously, and this could be, very, very small. This could be very tricky. You're going to want to choose A, not B. But if you look at this number and you have to choose something like A or B, you may think, I better go with the closest answer. And the closest answer to this calculator p-value is this smaller one, 0.0001, and that's not the case. This is the correct answer for the p-value. This mainly happens when you have such a big difference. When the test statistic falls off the z-table and you got to use the footnote information, you will have a difference, a pretty big difference between the p-value by hand and the p-value by calculator. And that's because the test statistic fell off the table. Or your test statistic is really, really small or really, really large, you're going to have a difference. So here I would be hoping that you know how to calculate the p-value by hand so that you could choose A. Now you would say, well, Ms. Manhart, don't put letter B there. The reason I put letter B is not because of the TI 8384 situation, but I want to get those people that are not going to double it and just leave it by as the 0.0001. So that's why I've got to put that there for people that will forget to double it when it's a two-tailed z-test. Now the next video is going to be on the two-tailed, the t-test for the true mean. And we'll decide out of the three, do I give you a two-tailed t-test, a left-tailed t-test, a right-tailed t-test, etc. With this particular video, remember, the only two that I showed you happened to be the first one was a right-tailed z-test, and this one is a two-tailed. So you'll need to write down that you will need to go over a problem that is a left-tailed z-test for the true mean. Left-tail meaning that when you set it up, it looks like this. And one of those would be your claim. So we did not do a left-tailed z-test. We didn't have that situation. So that's not represented. Thank